My presentation today is about cognitive load theory and related considerations in technology-based learning. According to cognitive load theory, cognitive architecture consists of two main components. First, working memory is our main processor of information with a very limited capacity and duration when dealing with novel, unorganized information. Second, effectively unlimited long-term memory that stores cognitive schemas that vary in their degree of complexity and automation. These two components of human cognitive architecture are closely interrelated with each other. Cognitive load can be defined as working memory resources required for completing a learning task or activity by learners with a specific level of prior knowledge. Higher levels of cognitive load are usually caused by learning tasks with highly novel or unorganized information. There are different types of cognitive load. Intrinsic cognitive load is the load that is relevant to achieving the intended learning goals. It depends on the degree of interactivity between essential elements of information and on the level of learner prior knowledge in long-term memory. Extraneous cognitive load is the load that is irrelevant to learning and is present only because instruction is designed in a way that requires learners to engage in cognitive processes and activities that are not actually required for acquisition of intended schemas. German cognitive load are the resources actually allocated by the learner to processing essential elements of instruction, or, in other words, to dealing with intrinsic cognitive load. The level of actually allocated resources, most importantly, German cognitive load, usually depends on learner motivation and engagement with the learning task. Cognitive load theory investigated quite a few phenomena and factors that inform instructional design in various learning environments, especially in technology-based learning. For example, with the modern technology innovations, nowadays it's very easy to transform written texts into spoken narrations and transform pictures into videos. People are getting very used to learning via watching video tutorials. However, both spoken words and visuals could disappear from learner auditory and visual sensory registers very rapidly and before they are integrated with the following information to achieve understanding. To deal with this, the learner must maintain the fleeting information in a temporary storage, which is the working memory, before the integration happens. Such processes may easily overwhelm working memory. To combat the possible negative consequences of transient information, learner-controlled pacing of presentation supplemented with segmenting materials into smaller sections could be helpful. High cognitive load can also be generated in situations when learners need to distribute their attention between several related sources and modes of information presentation that should be processed concurrently in working memory. Such environment can easily create split attention situations. Interestingly, some procedures and techniques may contribute to both reduction and increase in extraneous load. For example, allowing learners make their own decision on sequencing the content and pacing the presentation could reduce the extraneous cognitive load caused by information transiency. However, such design also requires additional working memory resources. Thus, specific conditions of effectiveness of different instructional methods, especially the learner readiness and characteristics, must be considered in each particular case instead of following a universal fixed set of principles or guidelines.